Astronomers have now unveiled the first image of a supermassive black hole located right at the center of our very own Milky Way galaxy.
To an amazing new look at the center of our galaxy. This fuzzy image of a supermassive black hole at the center of the...
When the James Webb Space Telescope first unfurled its golden mirrors and began scanning the cosmos, the astronomical community anticipated breakthroughs in deep field imaging, exoplanet analysis, and galaxy formation. Few, however, dared to dream that it would one day provide a direct visual glimpse into the heart of one of the universe's most enigmatic phenomena, a black hole. And yet, against all expectations, it has done exactly that. Before we start, smash the like and subscribe buttons for more updates. The moment arrived when the telescope was focusing on Sagittarius A*, the supermassive black hole at the center of our Milky Way galaxy. Nestled 26,000 light-years from Earth, Sagittarius A* has long captivated astrophysicists. Though its gravitational presence has been inferred by the swirling orbits of nearby stars, it had never been directly observed with clarity until now. Using its highly advanced infrared capabilities and unparalleled sensitivity, the James Webb Telescope managed to pierce through the dense cosmic dust clouds that shroud the galactic core and capture an image that redefined what humanity thought was observationally possible. This image, astonishing in its detail, doesn't show a void or a simple shadow against the backdrop of stars. Instead, it reveals the contorted space-time surrounding the black hole's event horizon, with gravitational lensing creating a warped halo of light, the photon ring. For the first time, the structure of this ring is visible with such clarity that individual arcs of infalling matter, spiraling ever closer to oblivion, can be seen with unprecedented resolution. What was once a theoretical sketch derived from Einstein's equations now appears as a cosmic reality. The image is not of the black hole's interior in the classical sense. No light escapes the event horizon, but it reveals the dynamic region just outside of it, the accretion disk, and the distorted space where the laws of physics are pushed to their limits. Through Webb's infrared eye, clouds of gas and plasma, heated to millions of degrees, spiral inward at relativistic speeds. The telescope captured the interplay of magnetism, gravity, and light in this cosmic maelstrom, offering an extraordinary glimpse of what lies just beyond the ultimate boundary. What makes this feat even more staggering is the precision with which the data was acquired. Webb's instruments had to be aligned with surgical accuracy to focus on the minuscule angular region occupied by Sagittarius A* from our vantage point. Combined with a series of long-duration exposures and careful calibration to eliminate noise and distortions, the image that emerged is as scientifically valuable as it is aesthetically profound. This is not just an image, it's a multi-layered spectrum of information, rich in data that will occupy researchers for decades to come. One of the most jaw-dropping features revealed by the image is the presence of a visible stream of matter appearing to plunge directly into the black hole. This observation has never before been visually confirmed. Theoretically, matter orbiting a black hole heats up and emits radiation as it loses angular momentum, eventually crossing the event horizon. But until now, this process has only been studied through indirect signals, bursts of X-rays, or sudden shifts in nearby star movement. Webb's image appears to show this dramatic act in progress, a luminous funnel of ionized material spiraling inward, twisting like a celestial tornado toward its inevitable doom. The implications of capturing such a scene are profound. For decades, black holes have served as the ultimate test of general relativity and the limits of known physics. Their extreme environments offer insights into quantum gravity, time dilation, and the nature of space-time itself. This image allows scientists to compare theoretical models of black hole behavior against actual, high-resolution data. Already, simulations based on Einstein's field equations are being updated to better reflect what Webb has revealed. Some of the differences are subtle, variations in brightness and arc curvature, but they are scientifically significant, hinting that there may be more to learn about how gravity behaves at cosmic extremes. Equally compelling is what the image suggests about the structure and behavior of accretion disks. Theories have long proposed that accretion disks are turbulent, magnetically active regions, with jets occasionally erupting at near-light speeds. Webb's image provides visual evidence of the disk's density waves, revealing clumps and filaments within the swirling material. Some parts appear brighter, possibly due to shock heating or magnetic reconnection events, while others fade into obscurity, perhaps cooling as they drift inward. These observations offer a treasure trove of data on how energy is generated and dissipated in one of the universe's most violent environments. Perhaps the most surreal aspect of the image is the way light behaves around the black hole. Light, bending under the immense gravitational pull, wraps around the event horizon multiple times, creating what's known as an Einstein ring. But what Webb captured is more than a simplistic ring. It's a lensed mosaic of warped starlight, distorted in complex patterns that reflect the underlying geometry of space-time itself. Each photon in that image took a path bent by gravity, and some traveled around the black hole more than once before reaching the telescope. This bending not only confirms general relativity with stunning fidelity, but also serves as a cosmic magnifying glass, revealing background stars and galaxies whose light has been twisted into view. The ability to peer so close to a black hole also brings into focus the extreme relativistic effects predicted by Einstein. Time dilation, where time effectively slows down under intense gravity, could potentially be observed by monitoring how matter behaves as it nears the event horizon. If researchers can track specific blobs of plasma or filaments of gas, they may detect changes in light frequency or motion that reflect this distortion of time. Such observations could serve as the first experimental measurements of general relativity in the wild, as it unfolds under conditions impossible to replicate on Earth. In this image, the border between visibility and invisibility is more than a line. It's a frontier between physics as we know it and the mystery that lies beyond. The event horizon, once a concept in equations, now stands as a real feature on a cosmic map, visible not through direct light, but through the gravitational artistry that light undergoes as it dances on the precipice of forever. The timing of this achievement is poetic. In a universe constantly expanding, where galaxies drift apart and the cosmic microwave background grows colder, capturing an image of a black hole is akin to photographing the eye of eternity. These objects, born from collapsed stars or primordial conditions, hold within them the secrets of the universe's beginning and perhaps its end. To observe one up close is not merely a technological accomplishment, it is a confrontation with the infinite. For astronomers, physicists, and philosophers alike, this image is a revelation. It validates decades of theory, confirms long-held suspicions, and opens new corridors of inquiry. But more than that, it offers a humbling reminder of humanity's place in the cosmos. A telescope, stationed 1,000,000 miles from Earth, tuned to a frequency invisible to the naked eye, has captured something that until now existed only in equations and imagination. The image may not show the literal inside of the black hole, nothing can, but it reveals the inner workings of the black hole's gravitational dominion in exquisite, terrifying beauty. The sense of movement, of chaos, of inevitability captured in that snapshot is as haunting as it is awe-inspiring. Every stream of light bent around the abyss, every spiral of plasma glowing in its death throes, every flicker of energy in that frame tells a story of cosmic forces playing out on a scale beyond comprehension. There's an emotional weight to the image that transcends its scientific importance. It speaks to a fundamental human longing to understand the unknown. For centuries, black holes represented the edge of knowledge, a boundary where mathematics failed and physical intuition broke down. To look upon their vicinity with clarity is to confront the great cosmic paradoxes. Infinite density within finite space, unstoppable collapse against the backdrop of expanding emptiness. What Webb has achieved is not just a technical feat, it's a symbolic act of piercing the veil that has long shrouded the universe's most mysterious objects. The telescope's sensitivity to infrared wavelengths, light stretched by the universe's expansion, allowed it to cut through not just physical barriers, but temporal ones as well. In capturing this image, we are not merely seeing a point in space, we are witnessing a moment in time, billions of years in the making, as if peering through a keyhole into the ancient, churning heart of the galaxy. The black hole is not a static void, but a dynamic engine, consuming matter and spewing out energy in patterns dictated by the fundamental laws of nature. Webb's image confirms that these laws still hold at the edge of the known, yet it also hints that there is more to discover. the symmetry of the light arcs, the intensity of the emissions, and the variability in brightness suggest a level of complexity that current models only begin to capture. Scientists are now sifting through the data embedded within this singular image, frequencies, polarizations, motion signatures, looking for anomalies, patterns, and confirmations. Each pixel is a payload of information, each shift in brightness a clue to how matter and energy behave in one of the most extreme environments known. The implications stretch across astrophysics, cosmology, quantum mechanics, and even theories of time and causality. There is something almost mythic about this achievement. In ancient times, humans looked up at the sky and invented stories to explain what they saw: gods, monsters, celestial battles. Now we look into the same sky with instruments born of science and find that reality is no less wondrous, no less dramatic. A black hole, once imagined as a devouring beast or a tear in the fabric of the universe, now appears in astonishing clarity, a monument to both destruction and revelation. As the world collectively gazes upon this image, one can't help but feel a shift. Not just in our understanding of black holes, but in our understanding of what is possible when curiosity is met with ingenuity. The James Webb Space Telescope has delivered a glimpse of the unreachable, made visible the invisible, and turned a page in humanity's exploration of the cosmos. What lies within a black hole remains hidden, but the curtain has been drawn back further than ever before. For the first time, we are not just imagining the edge, we are seeing it. Beyond the astonishing clarity of the James Webb Space Telescope's image of a black hole's surroundings lies an even deeper story, one of technology, cosmic violence, interstellar dynamics, and the reshaping of long-standing scientific frontiers. With the first authentic visual capture of what lies just outside the event horizon, humanity has not merely photographed a cosmic object. It has touched the fabric of an entirely alien domain, a space where time, light, and gravity behave in ways fundamentally different from our everyday understanding. The technological sophistication required to accomplish this feat cannot be overstated. The James Webb Telescope operates 1,000,000 miles away at the second Lagrange point, where gravitational forces from Earth and the Sun are balanced, allowing it to remain stable and undisturbed by thermal or atmospheric interference. Shielded by a multi-layered sun shield the size of a tennis court, Webb maintains a near absolute zero temperature essential for detecting the faintest whispers of infrared light from the universe's most remote and obscure locations. But capturing the black hole's edge involved more than just a passive snapshot. It demanded a rigorous application of time domain astronomy, a discipline that examines how celestial objects change over time. Because matter near a black hole is in constant flux, Webb's instruments had to be capable of taking rapid, repeated observations, stitching together transient phenomena like flares, infall spirals, and relativistic jets into a coherent, high-fidelity image. The final product is a result of composite layering, a mosaic of temporal windows that together depict a real-time story of chaos and transformation unfolding at relativistic speeds. Among the most intriguing discoveries in the captured image are subtle looping patterns within the inner accretion disk. These loops, resembling knots or twists of plasma, indicate the presence of powerful magnetic fields threading through the disk like invisible threads. Such magnetism not only guides the movement of matter, but accelerates particles to velocities approaching the speed of light. These observations confirm the role of magneto-hydrodynamic turbulence, a theory long debated as a central mechanism in the behavior of matter around black holes. In many ways, this image serves as a Rosetta Stone for black hole physics. For the first time, direct observation offers insights into how angular momentum is redistributed, how energy is converted into radiation, and how material either spirals inward into oblivion or is ejected outward in colossal jets. By decoding the shape, texture, and luminosity patterns seen in Webb's capture, scientists are now able to refine their models of disk viscosity, plasma density, and magnetic reconnection zones. Each of these aspects has implications far beyond a single black hole. They apply to galactic evolution, star formation rates, and even the growth of cosmic structure itself. One particularly groundbreaking aspect of the image is its potential to reveal clues about the spin of the black hole. A spinning black hole, described by the Kerr metric, drags the very fabric of spacetime around with it, a phenomenon known as frame dragging. The geometry of the photon ring, along with asymmetries in the accretion disk, can hint at how fast Sagittarius A* is rotating. This in turn provides information about its formation history and how much matter it has consumed over billions of years. Faster spins suggest prolonged, intense accretion periods. Slower ones may hint at chaotic feeding or past black hole mergers. The power of this image extends even further when considering its context within galactic dynamics. At the center of the Milky Way, Sagittarius A* serves as both anchor and engine. Its gravitational influence sculpts the orbits of stars in the central bulge, regulates the flow of interstellar gas, and likely plays a role in periodic galactic-scale feedback events. By directly observing its surroundings, astronomers can better understand the feedback loops that determine when galaxies form stars and when those processes are shut down. This connection between black holes and galaxy regulation is one of the most compelling discoveries in modern cosmology, and Webb's image deepens that link through observation rather than inference. Another fascinating element revealed in the image is the interaction between infalling matter and the background interstellar medium. As gas clouds spiral inward toward the event horizon, they often collide with existing material, creating shockwaves and bursts of high-energy radiation. Webb's instruments detected these collisions as infrared flashes, like sparks in the darkness, giving us a real-time look at the feeding habits of a supermassive black hole. These feeding events, sometimes sporadic and violent, appear in the image as bright, jagged streams with varying intensity, providing astronomers with clues about both the local environment and the chemical composition of the feeding material. Chemical fingerprints imprinted in the light curves of the captured image are another stunning consequence of Webb's capabilities. Molecules such as carbon monoxide, ionized iron, and heated silicates reveal themselves in spectral data, showing not only what materials are being consumed, but how those materials are processed before destruction. These elements contribute to the rich interplay of thermodynamics, particle acceleration, and radiative transport in and around the event horizon. Each spectral signature, frozen in the image, is a time capsule of cosmic alchemy at the universe's most dangerous threshold. This is not just a leap for astrophysics, it's a cultural and philosophical milestone. Humanity, a species born on a rocky planet orbiting a yellow star, has built a machine capable of resolving the fringes of an object from which light itself cannot escape. This image challenges our notions of visibility, perception, and physical boundaries. It forces a confrontation with questions that lie at the intersection of science and philosophy. What does it mean to see something that fundamentally defies observation? Where does reality end and theory begin? How do we define a place that has no surface, no volume, and no escape? Even as we marvel at the visible features of the black hole's edge, Webb's data allow a glimpse into temporal phenomena, capturing not just static forms, but evolving patterns. For instance, fluctuations in brightness across the accretion disk offer a window into the black hole's feeding rhythm. By observing how these variations change over hours and days, astronomers can track the formation and dissipation of hotspots, localized regions of higher energy within the disk. These hotspots spin rapidly, their motion revealing the inner disk speed and energy distribution. There is also the tantalizing potential to test aspects of quantum gravity. The image may contain tiny deviations from classical predictions, subtle enough to require high-precision modeling but present nonetheless. For instance, if the observed photon ring contains any anomalies in shape or thickness, it might hint at new physics beyond general relativity, perhaps involving quantum corrections to the fabric of space-time. While such conclusions require careful analysis and corroboration, the very possibility that this image holds traces of quantum gravity makes it a focal point for theoretical physicists worldwide. Among the most unexpected revelations are the gravitational lensing effects, not only from the black hole itself, but also from surrounding stellar remnants and dense gas clouds. These secondary lensing artifacts create a sort of nested visual structure within the image, multiple arcs, ghost images of stars, and warped galaxies that appear smeared across space. These features, while visually stunning, also serve as powerful tools for mapping mass distributions in the galactic core. By analyzing how light is bent, astronomers can chart the presence of invisible matter, likely dark matter, lurking near the black hole. Another frontier opened by this image lies in time dilation studies. Light emitted from the inner regions of the accretion disk experiences severe redshift due to the immense gravitational pull of the black hole. This redshift, literally the stretching of light to longer wavelengths, can be precisely measured in Webb's spectrum, revealing how strongly time is warped in the black hole's vicinity. By comparing light emitted at different distances from the event horizon, researchers can construct a gradient of time distortion, effectively mapping the rate at which time slows as one approaches the singularity. The data also speak volumes about the life cycle of black holes. Signs of previous mergers, hinted at by asymmetries in the disk and irregular gravitational field distortions, suggest that Sagittarius A** may have grown through collisions with other black holes or massive stellar objects. These echoes of ancient cataclysms are etched into the environment around the event horizon. They hint at a cosmic history of violence, where gravity shapes evolution through merger, collapse, and consumption. This image, then, is more than a snapshot. It is a history book written in photons, each one bent and aged by the gravitational tumult it endured. Some of the light-reaching Webb began its journey tens of thousands of years ago, twisted by the immense curvature of space and time near the black hole. In that light is the story of a galaxy's heart, a tale of formation, destruction, and rebirth on a scale that defies human measurement. It's easy to overlook the subtle but profound emotional weight that accompanies this achievement. To see something so unreachable, so fundamentally hostile to life and matter, is to confront a kind of sublime terror. And yet, that terror is tempered by awe, a sense that in capturing the image, we have glimpsed a fundamental truth of the universe. This is a place where the ordinary rules fall away, where up and down lose meaning, where the arrow of time may itself bend or even loop. And yet, even here, the light finds a way to tell its story. There is something paradoxical about how the black hole, an object defined by its invisibility, has become one of the most visual symbols of modern astronomy. Through Webb's lens, this icon of darkness has been rendered in color and contour, shape and structure. It has become legible, even familiar. In doing so, it bridges the gap between pure theory and tangible reality. No longer must we rely solely on artist impressions or computer-generated simulations. We now have a real recorded moment in which the edge of nothingness has come into view. The implications of this breakthrough are not limited to the scientific realm. They ripple into education, culture, media, and even the arts. Just as the first images of Earth from space reshaped how humanity saw itself, as a fragile sphere in a vast void, this image may come to redefine how we understand our place in the cosmic order. It marks a point where exploration transcends the physical and becomes conceptual, where observation meets imagination at the very threshold of the knowable universe. As scientists continue to dissect every pixel, spectrum, and variable embedded in the image, new theories will emerge, old assumptions will be challenged, and textbooks will be rewritten. But even as knowledge advances, the emotional resonance of this image will endure. It is not simply the result of scientific progress, but the culmination of a collective will to understand, to probe, to reach beyond. In the deepest reaches of space, where gravity becomes an all-consuming tyrant and light itself strains to escape, the James Webb Space Telescope has looked and seen, not into the black hole itself, but into its soul, its machinery, its chaos and elegance. What it has captured is a portrait not just of a celestial object, but of the cosmic forces that shape the destiny of stars, galaxies, and perhaps the universe itself. And in that light, bent, delayed, twisted, but ultimately delivered, we find a reflection of ourselves. Curious, bold, and unafraid to peer into the dark. What lies beyond the veil of that captured image is not only a landmark in observation, but a doorway to entirely new branches of cosmic inquiry. Branches that previously existed only as thought experiments, equations on a chalkboard, or speculative models in theoretical journals. The James Webb Space Telescope hasn't merely advanced our understanding of black holes, it has laid the foundation for the next generation of questions humanity must ask about the fabric of reality, causality, and the underlying architecture of the universe. Perhaps the most transformative aspect of Webb's image is its ability to act as a unifying data set across disciplines. For decades, black hole research was fragmented into categories. Observational astrophysics studied black hole candidates and high-energy events. Theoretical physicists examined singularities and event horizons, cosmologists considered their impact on galaxy formation, and particle physicists speculated about quantum behavior under extreme gravity. With a visual data source as robust and multidimensional as Webb's infrared image, these domains now converge. The image serves as a nexus, a focal point where multiple scientific languages translate into a single coherent narrative of a black hole's behavior. For example, gravitational theorists can now explore how space-time behaves not in approximation or simulation, but in raw visual reality. The symmetry, or subtle asymmetry, of the observed photon ring and the distortion in the accretion disk offers real-world data to test higher dimensional models, including brane-world scenarios, modified gravity frameworks, and emergent gravity theories. These models, which propose that gravity might not be a fundamental force but an emergent phenomenon, now have a proving ground. Webb's image isn't just a photograph. It's a testing chamber for the very laws of nature. Meanwhile, quantum field theorists have turned their attention to a phenomenon barely visible in the periphery of the image: Hawking radiation analogs. While true Hawking radiation, black body radiation emitted due to quantum effects near the event horizon, is still too faint to detect directly, the interplay of high-energy particles near the boundary might allow indirect inference of quantum effects at that edge. Tiny fluctuations in energy density observed in Webb's spectral data hint at interactions not fully accounted for in classical models. If confirmed, these anomalies could be the first observational signatures of quantum behavior on the edge of space-time collapse, opening the door to quantum gravity research in a way previously thought impossible. This image also challenges what we understand about the structure and behavior of space itself. The intense warping of background starlight reveals just how malleable space becomes near a black hole. Observing the way distant galaxies stretch, twist, and even appear duplicated around Sagittarius, A** has led researchers to refine their models of gravitational lensing to unprecedented accuracy. But there's more. Some light appears to spiral toward the observer not from behind the black hole, but from multiple orbits around it, a visual echo of paths taken in curved space-time. This recursive lensing, predicted but never directly seen, gives rise to the idea that light may carry a memory of its journey, a kind of photonic history encoded in its path and polarization. The potential to analyze that memory is monumental. By studying polarization vectors and redshift patterns of the light within the warped halo, scientists may be able to reconstruct the geometry of space-time at sub-Planckian scales. This is a step beyond general relativity, edging into the domain where gravity and quantum mechanics must coexist. It allows for the testing of conjectures like the holographic principle, an idea suggesting all information within a volume of space may be encoded on its boundary surface. If the geometry of the black hole's photon sphere can be decoded as a type of data storage surface, it would support the notion that reality is fundamentally informational in nature. Meanwhile, Webb's image reveals much about cosmic scale and proportion. Observing a region of space so dense and yet so compact places into perspective the dynamic range of mass and volume in the universe. A black hole with the mass of millions of suns compressed into a space smaller than our solar system demonstrates nature's extremes. Yet surrounding it is the bustling environment of the galactic core, regions thick with stars, clouds of gas, and turbulent magnetic fields. The juxtaposition of the black hole's dominion with the relatively stable orbiting regions around it paints a vivid picture of cosmic balance, a universe constantly balancing collapse against expansion, entropy against order. The Webb image has also drawn attention to the nature of causality in warped spacetime. Within the observable disk structure, there are regions where matter appears to spiral into no-return zones, with behaviors that mimic time loops, scenarios where events might unfold differently from the linear cause and effect relationships we know. This has led to renewed interest in closed time-like curves, theoretical paths through spacetime that allow for looping timelines. While these phenomena remain theoretical, the ability to now match them against visual patterns in real observational data brings them closer to scientific rigor. What was once purely speculative, narratives of time travel or relativistic paradoxes, now must be measured against what we see at the very edge of a black hole. Equally compelling is the way the black hole's gravitational influence acts as a telescope in its own right. The lensing effect reveals galaxies far beyond what Webb could detect on its own. Light bent around Sagittarius A** brings into view star systems and nebulae that otherwise lie in obscurity. These unexpected revelations offer a twofold benefit. Not only are we studying the black hole, but we're using it to study distant parts of the universe, creating an accidental observational synergy between the telescope and the object it observes. The sheer complexity of interpreting this image also emphasizes the rise of machine learning and AI in astrophysics. Analyzing the layers of data, luminosity shifts, wavelength variation, gravitational patterns, requires algorithms that can detect nuance beyond human capacity. These tools sift through petabytes of information to find meaningful correlations and anomalies. Webb's data has become a training ground for advanced computational models that could eventually become autonomous research assistants, capable of finding subtle deviations that even seasoned scientists might miss. In the broader scope of exploration, this image represents a new kind of frontier. Humanity has traditionally explored through movement, traveling to new lands, diving into oceans, ascending mountains, and launching into space. But this is an exploration of understanding, of resolving phenomena previously believed to be opaque by their very definition. It is a shift from physical travel to cognitive expansion, where our instruments act as surrogates for the senses and imagination becomes grounded in evidence. We are, in effect, peering over the edge of a conceptual cliff, seeing the invisible, mapping the unmeasurable. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on James Webb's first black hole image? What do you expect? We want to hear from you. Thank you for watching, and see you next time.